Okay, so in this next question we're asked for what value of the constant c is the function f continuous on negative infinity to infinity. And the function we're given is f of x equals cx squared plus 2x when x is less than 2, and f of x is equal to x cubed minus cx when x is greater than or equal to 2. So both of these functions on their own are continuous from negative infinity to infinity. But because they're piecewise defined, we have to make sure they're the same value at 2. And the reason that is because if they're not the same value at 2, then that means the left hand and the right hand limits would be different, meaning it would not be continuous at 2. So we're going to set these equations equal to each other because we want to make sure they're at the same value. So I'm going to do cx squared plus 2x equals x cubed minus cx. And because we want them to be the same value when x equals 2, I'm going to plug in 2 for x, and I'm going to solve for c. So I'm going to have c times 2 squared plus 2 times 2, and I'm going to set that equal to 2 cubed minus c times 2. Now if I evaluate this, I'm going to get 4c plus 4 equals 8 minus 2c. Now here I can add 2c to both sides, and I can also subtract 4 on both sides. So I'm going to get 6c equals 4. And then I can divide by 6, and I'll get c equals 4/6, which if you reduce that, it will end up being 2/3. So that would be your answer for that one. Okay, so in this next problem we're asked which of the following functions f has a removable discontinuity at a, and if the discontinuity is removable, find a function g that agrees with f for x does not equal a and is continuous at a. So basically what this is saying is we're given these three functions here, and it wants us to find which of them has a removable discontinuity at a, and then it wants us to find another function g that has the same values as f for all other values except a, but is also continuous at a. So for example, in this one, f of x equals x to the fourth minus 1 over x minus 1, our a equals 1, so in this case we'd get 1 minus 1 over 1 minus 1, which is 0 over 0, which is undefined. So that is a removable discontinuity. So that means that we're going to have to find a function g that agrees with this for every value that isn't a, but is also continuous at a. So in order to do that, if you remember, what we basically need to do is we need to find a way to simplify this fraction. And when I look at this numerator here, what I see is a difference of squares. I see a squared minus b squared, where our a is x squared and our b is 1. X squared squared is x to the fourth. That's basically what I'm getting at. So in order to factor that out, we can make it x squared minus 1, x squared plus 1. And now these two things, terms being multiplied by each other is the same thing as what's in the numerator. It's just a little bit simplified. And I can put that all over x minus 1. But we're not done yet, because x squared minus 1 is also a squared minus b squared, but this time our a is x. So when I go to factor this out, I'm going to have x minus 1, x plus 1 times x squared plus 1. And that's going to be all over x minus 1. And then so I can cancel out these x minus 1's here, and I'm left with x plus 1 times x squared plus 1. And that would be my new g of x function. Then in this one, we have f of x equals x cubed minus x squared minus 2x over x minus 2, and our a value now is 2. So if I go ahead and plug in 2 for x, on the numerator I'm going to get 8 minus 4 minus 4, which is 8 minus 8, which is 0. And then the bottom I'm going to get 2 minus 2. So once again, I'm in this 0 over 0 problem. So once again, I'm going to see what I can factor out. Now the first thing I see is that in the numerator we can factor out an x. And so what I'll be left with is x times x squared minus x minus 2 all over x minus 2. And then I can actually factor out this quadratic here. So I'll be looking for a number that two numbers that when multiplied give me negative 2, but when added give me negative 1. And the numbers that'll work for me there is x minus 2 and x plus 1. Negative 2 times 1 is negative 2, and negative 2 plus 1 is negative 1. So then I can cancel out this x minus 2 here, and I'll be left with x times x plus 1. And that would be my new g of x formula. Now for this last one, f of x equals the greatest value integer of sine x, and our a value is pi. Well, sine of pi is 0, and the greatest value integer that's less than or equal to 0 is 0. So there's no removable discontinuity here. We don't need to change anything with that. So that's how you do that problem. Use the intermediate value theorem to show that there is a root of the given equation in the specified interval. And the equation we're given is f of x equals x to the fourth plus x minus 3, and our interval is from 1 to 2. So remember, the intermediate value theorem says that if we have a continuous function, like let's just say we have a linear function like this, and I pick 2 points right here and right here, right? Then it says I'm going to have a value n, which if we draw our axes out here, and this is a very rough sketch by the way, it says we have a value n that's going to be between f of a, which is here, and f of b, which is here. And it says we have a number c, and so we'll have like f of c equals n basically. So if you have this continuous function and you have 2 points, there's a c value between those 2 points that will give you a f of c value that's between the f of a and f of b value, if that makes any sense. Basically what that means for us is that we have to prove that a root which is a 0, we have to prove that there's that this function will have the value 0 between 1 and 2. And the way we do that is we prove that f of 1 is negative, or f of 1 is less than 0, and f of 2 is greater than 0, or the other way around. If f of 2 is less than 0 and f of 1 is greater than 0, it still gets our point across because because we know that f of x is continuous on the interval negative infinity to infinity, so there's not going to be any point on the graph where it jumps from one value to another. So we know that if we can prove that it's less than 0 at a certain point and greater than 0 at a certain point, then at some point in between it has to be 0. So what I'm going to do is I'm going to do f of 1, and that's going to be 1 to the fourth plus 1 minus 3. 1 to the fourth is 1, and so we're going to have 1 plus 1 minus 3, which is 2 minus 3, which is negative 1. So right there we have a point that's less than 0, and that's f of 1. So let's see what f of 2 is. F of 2 is going to be 2 to the fourth plus 2 minus 3. 2 to the fourth is 16. So we have 16 plus 2 minus 3, which is 18 minus 3, which is 15. So right here we've proved that at f of 1 it's less than 0 and f of 2 is greater than 0. So we know at some point in between it will be 0. We don't actually have to find that point, we just have to state that there is that point. So you would have to write this down, but I'm not going to because it would take a long time to write down. But basically what you would write down is, by the intermediate value theorem, or by the IVT, there is some point C, and you would write it like this: there is some point C in 1, 2 such that f of c equals n. And n would be, no, it would just be f of c equals n. Yeah, that would be your final answer, basically. Okay, so in this next question, we're asked to do the exact same thing, except now our function is f of x equals cosine of x minus x, and our interval is 0 to 1. So I'm going to do just what I did last time. I'm going to start with f of 0. I'm going to have f of 0 equals cosine of 0 minus 0. Cosine of 0 is 1, minus 0, and then we're going to be left with minus 0, and 1 minus 0 is 1. So f of 0 is 1. And then if we do f of 1, so now I'm going to do f of 1, and that's going to be f of 1 equals cosine of 1 minus 1. And even though we don't know what cosine of 1 is without a calculator, we can still evaluate it by making somewhat of a guesstimate. And to do that, I'm going to draw a rough sketch of the graph of cosine of 1, or just cosine of x, I mean. So cosine of x starts at positive 1, and at pi, which we'll denote as being right here, at pi it reaches negative 1. So it goes like this. Rather, it goes like this, reaches negative 1 at pi, and goes up like that. Now pi is 3.14, and then a bunch of numbers after that. We can see though that it looks like cosine of 1 would be less than 1. That it would be something less than 1 minus 1, which would give us a negative answer. Now I don't know exactly what that negative answer is, but just to reinforce this idea, I do have a calculator with me, and I am going to do cosine of 1 minus 1. Cosine of 1 minus 1 is negative 0.45. So we have negative 0.45 there, and so we can see now that if f of 0 is 1 and f of 1 is negative 0.45, and this is a continuous function, then by the intermediate value theorem, there has to be some number c in the interval 0 to 1 such that f of c equals n. And there would be a root to this function, so that's how you do that one.